All right, so thanks everyone for sticking around until Thursday afternoon. My name's Sam Stanwyck. I'm from the quantum team at NVIDIA. And on the first day of this conference, I saw a panel where there was a question about if we should expect or be worried about a quantum winter. And I really liked the consensus answer, which is if there's a season that's the best fit, it's spring. And to me, I agree, and it's because of the amazing progress in quantum hardware we've seen in the past year, culminating in some really exciting announcements this week, and specifically in quantum error correction. I'm really excited that we're making the transition from NISQ systems with tens or maybe 100 qubits to really doing experiments with logical qubits and starting to scale those up. And so that's what we're trying to enable at NVIDIA, and that's what I'll talk about today. So to get there, I think it's useful to start with a North Star, where we're going, and we're calling that the accelerated quantum supercomputer. And I think the word hybrid is almost meaningless at this point. All quantum algorithms will be hybrid, quantum applications will be hybrid. But what useful quantum computing is going to look like is QPUs following something similar to the path that GPUs followed, where they get integrated into supercomputers that previously only consisted of CPUs and now consist of CPUs and GPUs. And the quantum computer will accelerate certain parts of the calculation, and the benefits will be reciprocal. So the supercomputer is going to be useful for getting the most out of the quantum computer, including with quantum error correction. And supercomputing is also going to be critical to get to that North Star. So not only will kind of the final picture with useful quantum computing involve supercomputing for error correction, but the fundamental research along the way is being enabled and is going to be enabled by accelerated computing, by GPUs, by AI. So everything from powerful simulations of different forms, digital twins of quantum computers, to error correction research itself. And so the way we think about what we're doing at NVIDIA is building the right tools on top of the accelerated computing platform we already have to enable the quantum computing research and breakthroughs necessary to get to that useful, fault-tolerant, accelerated quantum supercomputer. And this is our platform. It starts with Q2Q. And so about 20 years ago, NVIDIA introduced software called CUDA that made it so if you knew how to program in C, or eventually C++ or Python or many other languages, you could use a GPU. And this enabled integration of GPUs for scientific computing and into previously CPU-only supercomputers. We believe that quantum computers need to take a similar path, and so we've introduced Q2Q. Q2Q is open source. It's hardware agnostic. It extends Python and C++ with quantum kernels, so you can write code combining the best of quantum with GPU supercomputing and with AI, and run it on the most useful platform, be that a state vector tensor network simulator or quantum hardware where we're now integrated with many partners and more always coming. And it's an open platform available at many different levels. We release our simulation primitives separately in a library called cuQuantum. We build a reference architecture called DGX Quantum that's also available separately, and this means we're able to integrate with and accelerate nearly everyone in the quantum ecosystem. And so we're very proud to say that almost every leading quantum startup is building on NVIDIA in some way. Almost every framework is accelerated by our libraries, and almost every QPU that's getting deployed is integrating or already integrated with Q2Q. We count over 160 quantum partners overall, and this number is always growing. So that's a little bit of background on NVIDIA. Let's talk about how we get from what we have today, which is, I'd say, always improving qubits to this future of accelerated quantum supercomputers. There are a lot of challenges along the way and a lot of milestones to be achieved. We need to have better quantum hardware, both scaling up and improving fidelity. We need to develop better algorithms. So when we get to this system on the right, we know what to do with it for useful problems, and we can maybe even reduce the timeline to useful quantum computing by developing more efficient algorithms. We need to implement quantum error correction. That will be most of this talk. And then there are infrastructure challenges to building a system like this that we need to tackle. There are more challenges, but these are some of the big ones. And we strongly believe that AI supercomputing is going to be essential to help with all of them. For better quantum hardware, we've released software for simulations of open quantum systems and EDA tools for quantum that are now being used by Google and others to simulate and better design their QPUs. We have collaborations with many groups developing better algorithms, often combining AI to improve them. We believe AI supercomputing is going to be essential for quantum error correction. And then in the final picture, quantum will be integrated into the AI supercomputer to accelerate it. So it really, we feel like we're going to be able to help with kind of the whole picture here. And so for this talk, I'm going to focus on implementing QEC. If you're interested in the rest of it, you should check out my colleague, or hopefully you saw my colleague Elitsa Kioseva's talk on Tuesday, or if not, check it out when it's posted to YouTube. So before we dive into error correction, I think there's a lot of kind of talk of quantum computing and AI and their intersection. And so I wanted to kind of take a brief detour to talk about how we see that. And so there are two ways that quantum computing and AI can interact. Quantum computing can enable better AI. There's some promise to this. There are some good reasons to think it'll be very challenging. AI, at least the way it's done today, is very much a big data, big compute problem. Quantum computing is a small data, big compute solution. And so data loading is very tricky. But this is important research. But can AI enable better quantum computing? Well, it's already happening. And I think we're just scratching the surface. So in the last year or two, we've seen AI being used for optimal control of quantum computers to boost fidelity, for calibrating quantum processors. In the last month, Google released their alpha qubit paper using AI for quantum error correction. And so this is really an accelerating trend that we're very excited about. You know, as far as NVIDIA's role, we're a platform company. We try to make our partners successful. And so for making AI supercomputing useful for quantum error correction, what we think about is how do we build the right platforms? And for us, that takes two main form factors. One is hardware. So we need the right hardware systems. And for quantum error correction, the kind of key figure of merit there is low latency. So quantum error correction needs to be able to keep up with the quantum processor so that errors don't accumulate. Depending on your qubit modality, this can be quite fast, much faster than kind of using a GPU out of the box would be able to, or a GPU system out of the box would be able to handle. And so we need a platform to enable this. There's also not really mature software yet for quantum error correction research, and especially for making the best use of today's most powerful computers for quantum error correction and quantum error correction decoding. So for the most important things NVIDIA can do to help enable this, this is really where we're focused. And so we announced a system last year to address the first point called DGX Quantum. And this is a reference architecture for integrating quantum computers with GPUs and eventually with AI supercomputers. So it consists of a control system built by quantum machines, coupled through a PCIe Gen 5 interconnect to our Grace Hopper CPU plus GPU superchip. And there's a lot of kind of innovation in the full stack that went into this. Things like running a persistent CUDA kernel to avoid launch latency, and really kind of thinking at the whole system level about how to drive latency down as low as possible, to kind of have a building block to do physical quantum error correction research on GPUs. DGX Quantum is now deployed, the very first one, at the Israeli National Quantum Center, and we're seeing some exciting results already. So the picture on the left is a benchmark on a scope where we're looking at round-trip GPU-QPU latency, where we're sending some data from the QPU, doing some simple operation on the GPU, and sending it back. This is kind of a baseline of the latency that's achievable if you wanted to do decoding, and we're under 4 microseconds. If you kind of naively integrated and didn't optimize for latency, you'd likely be looking at least tens, probably hundreds of microseconds or more. And so we're very excited about this number. Depending on your qubit platform and your scheme, it's close to below or well below kind of the baseline where you can think about doing accelerated quantum error correction. And the second plot here is optimal control. So this is using an OpenAI reinforcement learning model to tune up a single qubit on a Rigetti 9-qubit processor. So I don't want to oversell this. This is a pretty simple task. This is not something that you couldn't do in another way. But we're using an out-of-the-box reinforcement learning model to tune it up in real time through DGX Quantum. And frankly, the fact that it works at all is amazing and really promising for much more complex control tasks with many, many more qubits, where you could see an advantage over other methods. So we're just getting started with this, but we're very excited about the initial results. And the second part of this is software. So on top of CUDA-Q, we've just announced CUDA-Q libraries, which consist of optimized kernels and some tools to help researchers and developers who want to use CUDA-Q for error correction and other things to kind of easily pick it up and make best use of it. So we have 2 libraries today. The first one is solvers, which is optimized hybrid solvers. The second one is a quantum error correction library called CUDA-Q QEC. That library consists of some pre-built and optimized codes and decoders written in CUDA-Q for you to just use, and really most importantly, an extension point, so that if you're doing error correction research, you can define your own custom codes and decoders, have them execute in CUDA-Q, run on your own system or a system like DGX Quantum. We have a built-in stabilizer simulator. It's STIM from Google. And this is all open source. And so in the last part of this talk, I want to share some exciting results that are already happening with our platform. And so I hope you got to catch Matt Kinsella from Inflection's talk yesterday, which went into this in much more detail. If you didn't, long story short, Inflection was able to run a logical qubit experiment where they see dramatic improvement in logical fidelities over the physical qubit fidelities, looking at a material science application, the Anderson impurity model. And this was enabled by CUDA-Q. So I can get the video going. All right, well, the video may not work, but it would just kind of show you what the code looked like. But they used a bunch of unique features of our platform including simulation tools. So in this case, GPU-accelerated simulations, emulating multiple QPUs, the Q2Q libraries, actually QEC and solvers for the optimized VQE kernels, and kind of a really important feature of Q2Q, the ability to accurately emulate a quantum processor with a custom noise model, custom gate operations, and then switch over to running on the physical quantum processor itself, simply by changing a compiler flag or a program argument. And then things like mid-circuit measurement and conditional logic for the quantum error correction. Oh, there we go. And enabling work like this is exactly why we built Q2Q. All right, we got past it. Enabling work like this is exactly why we built Q2Q, and we also built it with the intention of making it available to everyone to play around with. So we're very excited also to announce that Inflection has made all the code that was used to run that available for use today at this site. And they've also opened up pre-registration for access to their quantum processor that this was run on, where you can use Q2Q, and that's here. And they're expecting to offer that later on in 2025. So to kind of wrap it up, I think it's been an incredible year in quantum computing, and the part that I'm most excited about is all of the progress made in quantum error correction from many different groups. And at NVIDIA, we think that we can help a lot in taking the next step to scaling this from experiments on 2 or a few logical qubits to hundreds or thousands of logical qubits. We're building the hardware and software platforms to enable that, and working with the leading groups to help accelerate their work. So thank you for your attention, and take questions if there's time.
Yeah, we have time for a couple questions.
Oh, it's on. Okay, great. So you presented that very impressive latency number for the communication between the GPU and the QPU. Can you talk at all about sort of where the bottlenecks for that is? Or is it in the classical computation? Is it in the communication overheads?
Yeah, so the classical computation in that benchmark is trivial. There's not an actual decoding routine happening, so that would be added on. But the other bottlenecks are first of all the physical interconnect. So something like Ethernet, you might get 10 microseconds or more. Grace Hopper just happens to have a way to connect external systems with PCIe, which is much lower latency, and OPX has built a NIC for interfacing there. The second bottleneck you would usually see is data transfer from the CPU to the GPU. Grace Hopper is actually a really nice platform for this. Grace is a CPU, Hopper is a GPU. They have coherent memory, so you can actually land data in the CPU and operate on it with the GPU with much more quickly than you could in some other type of system. And the third is the launch latency of a CUDA kernel. So usually, if you're training a big AI model, you maybe don't care about a few microseconds at the beginning. What's happening in the software here is we're running a persistent CUDA kernel all the time, polling for data landing in certain parts of CPU memory and immediately operating on it. So we're able to save that overhead, and of course that would go away if you're constantly doing error correction, keeping up with the QPU. So those were the 3 biggest.
Any more questions? If not, let's thank our speaker.